So hello, this is problem number 12 of section 2.4 of our textbook Advanced Calculus by Patrick Fitzpatrick, second edition. Um, it starts out by saying let C be positive and define xn recursively by fixing x1 positive and xn plus 1 equals the square root of C plus xn. That means x2 is square root of C plus x1, x3 is C plus x2, square root of C plus x2, and so on and so forth. So it says, so they want us to prove that xn is a convergent sequence, and it converges to the solution, to the positive solution of x squared minus x minus c equals 0. Okay, for the positive solution. So we'll prove that xn is a monotone sequence and is bounded. Showing the monotonicity, I kind of wrote it here so we can just, I like to shorten the video a little bit. So suppose x2 equals x1. And now for the induction hypothesis, let's suppose that xn plus 1 equals xn. Then xn plus 2, which by definition is the square root of C plus xn plus 1, since xn plus 1 is the same as xn, this expression equals this expression. C plus xn plus 1 the square root of is equal to the square root of C plus xn. But this is xn plus 1. So xn plus 2 equals xn plus 1. And therefore xn is the constant function, the constant sequence x1 for all n. Alright. Now let's so basically what I did is that x2 equals x1. So if x2 is x1, then x3 will be equal to x2. If x3 equals x2, then x4 equals x3, and so on and so forth. Now for the second assumption, for the second case, suppose x2 is greater than x1, and we'd like to prove that xn plus 1 is greater than xn for each n. Well, what's xn plus 2? By definition, it's equal to C plus xn plus 1 the square root of. But xn plus 1 is greater than xn because those terms are all positive. The square root of C plus xn plus 1 is greater than the square root of C plus xn, which is really, by definition, xn plus 1. So xn plus 2 is greater than xn plus 1. Now, what that means is xn is an increasing sequence. The third is assuming x2 is less than x1. We like to show xn plus 2 is less than xn plus 1, assuming xn is plus 1 is less than xn. Well, let's let xn plus 1 less than xn. Do the same again. Write xn plus 2 in terms of xn plus 1, and xn plus 1 is less than xn. So that gives you xn plus 1 is greater than xn plus 2. So xn is a decreasing sequence. So in all cases, xn is a monotone sequence. So what's left is to show that xn is a bounded sequence. So we'll show that xn is bounded. Well, if it is a constant sequence, it's obviously bounded. So it's actually convergent, so there's no problem. If it's a decreasing sequence, since each term is positive, it's obviously bounded. Okay, so each term is positive, but it's a decreasing sequence, so bounded. So the only thing to show is what happens if it's an increasing sequence. Okay, so to show that xn is bounded, we will consider the case when xn is increasing. Okay, so let's look at xn plus 1. which equals the square root of c plus xn by definition. So this implies that xn plus 1 squared is c plus xn. But this is greater than xn squared. Let me back up a little bit. So xn plus 1 is the square root of c plus xn, and we know that xn plus 1 is greater than xn. So square both sides to get c plus xn is greater than xn squared. Okay, so this implies that xn squared is less than c plus xn, which implies that xn squared minus xn is less than c, which implies that xn times xn minus 1 is less than c. Now, if xn is less than 1, then it's less than 1, so it's bounded by 1. So if xn is less than 1, there's no problem, xn is less than 1. So if xn is greater than 1, then xn minus 1 is greater than 0, right? So what happens here? If you do xn minus 1 times xn minus 1, this guy is less than xn times xn minus 1, because xn minus 1 is less than xn. Okay, so xn minus 1 is less than xn, so xn minus 1 times xn minus 1 is less than, this guy is less than c, that's less than c here. This guy is, on the other hand, the left is a square of xn minus 1, that's less than c. This means that xn minus 1, let me do this again, xn minus 1 is less than c squared. So xn is less than 1 plus c squared. So we have shown that xn is bounded. So it is convergent. Therefore, xn is convergent. So we showed that xn is bounded by, first we showed that xn is a monotone sequence, and then we showed that it is bounded, particularly if it's increasing. If it's decreasing, it's bounded, obviously. If it's a constant function, it's bounded. So we showed that it is bounded, so it is convergent. Now, next thing to do is to show that the sequence converges to the solution of this quadratic equation. Well, let's see. All right, okay, let's see how we can do that. Well, now suppose that the sequence xn converges to x. That means that the limit of xn as n approaches to infinity is x. In fact, the limit of the nth term goes to x means the limit of the next term also goes to x. So the limit of xn plus 1 as n approaches to infinity is also x. Okay? So what happens here? xn plus 1 is squared is c plus xn. Take the limit of xn plus 1 squared. Take the limit of xn plus 1 squared. Which is the limit of c plus xn as n approach to infinity. Well, this guy is c plus x because the limit of xn is x. And this guy here is the limit of xn plus 1 squared, which is really x squared. So x squared is c plus x, or x squared minus x minus c equals 0. And therefore the sequence xn converges to the solution of x squared minus x minus c equals 0. Obviously, since the terms are all positive, they can only converge to the positive solution of x squared minus x minus c. So that ends the proof of the question, the problem. So they want us to prove that xn is convergent, and it converges to the solution of x squared minus x minus c equals 0. All right, well, thank you. I hope this was clear enough, and take care.